Beautifully constructed online math lesson. I'm your host, Miss Lambert, coming to you live from my bedroom in my comfy chair. Okay, today we're going to talk about a bunch of different ways that we can represent data. Therefore, it is called data representation. The first thing that I want to go over with you is called the sample space. And a sample space is basically just a list of all possible outcomes in like a probability experiment. And so one of the ways that we're going to list the sample space is with a tree diagram. I think you've seen this in like 7th grade, maybe. But it's been a while. So here's what we're going to do. With this tree diagram, I'm going to do an example where we're going to flip a coin, and then we're going to spin a 3-colored spinner that's divided into equal sections. I think tree diagrams are kind of fun because it's basically an illustrated version of Choose Your Own Adventure, where here's your point of decision, the first point, and now I'm going to branch off with the choices, or I guess the possible outcomes of my first event. So with flipping a coin, well, my possible outcomes are heads or tails. Great. Well, now we're going to branch off of both of those and do the possible outcomes of my second event. So let's say my 3 colors are going to be, red, yellow, and blue. Red, yellow, blue. Great. That's my tree diagram. And basically this represents the sample space because basically each different branch path is a different outcome. So if I follow the very top, that's going to be heads red, and then heads yellow, heads blue, tails red, tails yellow, tails blue. So this could be a representation of my sample space if I just list them out. We don't have to list them out if we have the tree diagram because the tree diagram itself does show what your sample space could be. The only other thing that we can add to this tree diagram would be the probabilities for each branch, where sometimes that's required, sometimes it's not. But for the first event, well, I know my probability of heads or tails, well, that's half. I could list that as 1/2, or I can put it as a decimal. Math space, I think, prefers fractions because then, like, I tried it and I tried rounding one of my decimals that was like going on forever and it didn't accept it. So I would suggest keeping everything as fractions. So then with my spinner, I know all my probabilities are going to be 1/3. Okay, so now with this, we're going to go over a few rules. First up is the multiplication rule. Here's what this says. The probability of 2 things happening, because remember this intersection could also be substituted with the word and. So probability of events A and B happening, all I'm going to do is take the probability of A and multiply it by the probability of B. So let's do an example of that. I wanted to switch color. Okay, I want to find the probability of getting a heads and spinning yellow. Well, I can look at this in 2 ways. First, I'm going to do the way that, we just went through with the rule, where the probability of heads I can see from my diagram is 1/2, and the probability of yellow is 1/3. With fractions, we multiply straight across, and we get 1/6. I can check that over here in my list and say, oh, look, there are 6 possible options. There's only 1 option where I'm getting heads and yellow, so 1/6 would be correct. The next rule that I want to go over with you is the addition rule. So if you want the probability of event A or event B happening, we can add the two probabilities together, but we're going to have to subtract that intersection, because basically what happens there, and this will be more clear in the two-way tables that are going to come up on the next slide, is if we don't subtract that layer of intersection, that means we're double counting those options. So, for example, if I want the probability of tails or getting blue, well, tails I know is half, blue is 1/3, but I have to subtract, well, what is it to get blue and 1/3? Wow, I said that wrong. The probability of getting tails and blue. Right there, that's 1 out of 6. I want to erase that. No, I don't. Just kidding. Whatever. We're moving on. Okay. So I'm going to get a common denominator for everything. 3, 6 plus 2, 6 minus 1, 6. 3 plus 2 is 5 minus 1 is 4 out of 6, which we're going to get 2/3. Well, let's check that with our sample space to make sure we got that. So anything with tails, and now anything with blue. You see how if I had just done anything with blue, I would have double counted that guy down at the bottom. So that's why we subtracted that 1/6 option right here. But yeah, I can see, oh, there's 1, 2, 3, 4 out of 6, which reduces to 2/3. Cool. Math works. That's what we're learning. Great. I want to do one more example just to make sure we got it. Let's say, what is the probability of just being red? Well, you see how red is represented in 2 different branches, and so we have to calculate the probability following the branches. And I know for this example, at least if it's me, I'd be looking here at the sample space going, oh, it's 2 out of 6, which is 1/3. But sometimes we have a pretty easy example because all of our probabilities were the same for each branch. But one of your math space homework questions, they have different probabilities on some of those branches. So I want to show you what to do in that case, where basically you just got to follow the branch all the way through. Where probability of red, I'm going to use red, well, I know I can either go tails and then red to get to here, or I can go heads and red to get to there. And I know that following those branches, we're going to use multiplication. So the first bit, I'm going to start with the top one. I got 1/2 times 1/3. And I'm going to take that and do another 1/2 times 1/3. So, like we already figured out, we knew it was going to be 2 out of 6, which is 1/3. But I want you to just see that you're going to have to follow the branches in some of them.